Hello, Daniel. We're waiting for you. Okay, since Daniel is not here, Henry, can you help us with what we did in last class I had with you guys?
Good morning, Mr. Timmy. I'm sorry, I haven't gone through the recordings from the last class. I'll hopefully do that today because the recordings were shared with us yesterday. So
Okay, no problem. Can anyone just give a brief recap of what we did in the last class we had together? Okay, Okoli is raising up his hand.
Yeah, good afternoon.
Yeah, good afternoon.
Yeah, the last class you had with us, I think that was Monday. You introduced the Hadoop ecosystem. Taught us the different tools. All the major ones there. You mentioned the yarn, there was yarn, and then the other two I can't really remember. But then you taught us the other components. You also have Scoop, Uzi, Flume, and the likes. So that was all you covered the last class on Monday. Just introduction to the Hadoop ecosystem, the functionalities of the different components, and what you can use them to do.
Okay, thank you very much, Okoli. Okay. So the last class I had with you guys on Monday, just like as Okoli has explained to us. So I introduced us to I gave a brief concerning the Hadoop 2 ecosystem. So I taught us about the different components of the Hadoop 2 if you notice, I'm saying Hadoop 2 ecosystem. There is Hadoop 1 and there is Hadoop 2. So Hadoop 2 is more of the recent updated Hadoop ecosystem that we have, whereby some bugs and errors some things we couldn't do in the Hadoop 1 ecosystem have been fixed and have been implemented in Hadoop 2. Then in that same class also, I made us to understand that we have three major components of the Hadoop 2 ecosystem. But I'm going to take it like this today now. So I'll first talk about the Hadoop 1 ecosystem. Then I would now talk about the Hadoop 2 ecosystem. So the original Hadoop ecosystem, it came with just two major components, which is the HDFS and the MapReduce. So the HDFS is the Hadoop distributed file system, and you also have the MapReduce, which is the compute engine for the Hadoop, the compute engine framework for Hadoop. Then in Hadoop 2, because of the bugs and in Hadoop 1, we're actually giving a lot of work to the MapReduce compute engine framework to do. So they lifted some things off from it and they implemented some new options and some new functionalities in Hadoop 2 ecosystem. That was when the yarn software layer framework was introduced into the Hadoop ecosystem. So now the current Hadoop ecosystem we have, which is the Hadoop 2 ecosystem, we have three major components. We still have our HDFS, we have our MapReduce, and now we have the yarn. So before in Hadoop 1 ecosystem, normally the MapReduce used to do some sort of the major administrative work of coordinating the processes in the ecosystem and coordinating the activities of the HDFS. But now in Hadoop 2 ecosystem, with the presence of our yarn, so that part of that task has been lifted up from our MapReduce and has been given to the yarn. So the yarn is now the one responsible for your global resource management and your application management also. So it is the yarn that is responsible for it now. So yarn also means yet another response negotiator. I would explain that in detail later. So today, what we will be doing today is we'll be talking about the different frameworks for processing on Hadoop. So we'll be talking about the different frameworks for processing on Hadoop. So like I told you in the last class, in the Hadoop ecosystem, we have a lot of components, a lot of elements and the rest. But still, you need to take note. If you are being asked for the major component of the Hadoop 2 ecosystem, you have the HDFS, which is the Hadoop Distributed File System. You have the MapReduce, and then you have the yarn. But if it's just a normal question that asks you that, okay, what are the major components of the Hadoop ecosystem? That's when you will just refer to the HDFS and the MapReduce. You need to take note of that. If I use Hadoop 2 in my question, or maybe in your certification exam, if Hadoop 2 is being used, then you can call those three, which is HDFS, MapReduce, and yarn. But if it's just the Hadoop ecosystem, the major components there are just the HDFS and the yarn. So then also I iterated in the last class that we have other components that we use in interacting in the Hadoop ecosystem. I made mention of the HBase. Then I made us to understand that the HBase is more or less like your normal database, but it gives priority to the columnar database system and monitoring. Then it also gives room for timestamp and versioning. Then I also made you to understand that you can use HBase in your Hadoop ecosystem with other client softwares and client tools, making use of your Java APIs. I treated that in last class. Then I also spoke about your Hive. Then I made you to understand that your Hive, you can use your Hive for your major ETL processes and the likes. That with your Hive, you can make queries in your SQL programming language and you also get results. That is possible because of an implementation of the Hive in SQL, which is your HiveQL. Then I also made mention of other components and elements we use in interacting with the Hadoop. I made mention of the Flume, the Zookeeper, the Uzi, just like as Okulia has told us earlier. So today we'll be going a little bit deeper in understanding the frameworks we use for processing in the Hadoop ecosystem. Okay, so I'm going to be sharing the screen first.
Thank you very much for recapping, sir.
Okay, you're welcome. Please let me know if you can see my screen.
Yeah, we can see.
Okay,
I can
thank
see.
you. Okay, so like I said, today we'll be looking at the different frameworks used for processing in the Hadoop ecosystem. So basically today we'll be giving priority to looking at the major components of our Hadoop ecosystem. We'll be looking at, okay, we looked at HDFS in detail in our last class, where I told you guys about the Hadoop cluster, the different commodity servers which you can refer to as your data blocks. Then I told you guys about the name node, the data node. Then I also spoke about the different processes and different functionalities of your name node and data node. All of those things I was explaining about the name node and data node. Most of all those things are functionalities that comes with the Hadoop distribution file system with your HDFS. So today I'll be going in detail looking at the functionalities of your MapReduce. Why did they have to come up with building a solution like MapReduce? Why was it built? Why was it invented? Then I'll also be taking us further looking at the yarn, the functionalities of the yarn. What does the yarn do in detail? Characteristics of functionalities of what yarn does. Then I'll also be touching some few aspects of your HBase. Remember I spoke about the HBase being a data, more or less like your normal database management system, but it is not the same thing as your relational database management system, because it has versioning, and it also has the timestamp functionality also, and you can also you can interact with your HBase using your Java API. That's how it is different from your normal RDBMS. Then I'll also be talking about your Hive. I'll be talking about using your Hive for data mining activities and for deep analytics. Then after that, I'll just give a brief summary of everything so far, the major points you shouldn't forget, and during the class we'll also be touching some few questions like that as we go on. So I already explained the objective of today's class. Okay, so now let us talk about MapReduce. So I want you guys to look at it this way. Please let me know if I'm getting too technical, but I'll try my best to explain these things in simple terms as I can so that you will see it. Okay, so let me talk about the origin of MapReduce. If I'm going to talk about MapReduce and the broad functionalities of MapReduce, I would have to refer to the very first Hadoop ecosystem, which is your Hadoop 1.x. I'll have to refer to everything that the MapReduce was created to build. And just as the name indicates, the MapReduce compute engine framework was built based on the MapReduce algorithm. I'm sure you've heard of different data structures and algorithms like your time complexity, ON complexity, and the rest. But this one, MapReduce, was built based on the MapReduce algorithm. And what does this MapReduce algorithm, what does it necessarily imply? If you can remember, in the very, I would say the second class here, probably most likely the second class you guys had, they taught you guys about distributed processing, distributed computing, parallel computing, and the rest like that. So everything about distributed computing, parallel computing, so that's the technology that actually drives the MapReduce. So in simple layman language, I would say MapReduce is, okay, I have a task I have an operation to carry out now. So that operation, I'm going to share it into different bits of tasks. Let's say like 10 different tasks. Then those different tasks, I'll now give it to different processors. So meaning I have a major task. So I'm mapping that major task to different processors to work on for me, just like your distributed computing or your parallel computing. Funnily enough, if those processors are sharing the same memory, that's when we refer to it as parallel computing. But if those processors are using different memories, that's when we refer to it as distributed computing. And in distributed computing, the latency is not as good as when it is parallel computing. I'm sure you guys understand what I mean by latency here. It means like in parallel computing, when the memory and the processors are in the same cluster, in the same domain, it's easier for data to travel faster. Time is reduced, data leakage is also avoided, data security is also assured. So going by your MapReduce, I've already mapped out my major operation into different sets of tasks, and I've given it to different processors to try to carry it out for me. So what would my map algorithm do? So my map algorithm has already shared everything now. So those different processors will work on that task. After working on their own task, so meaning those different processors now, if you remember when I was explaining the HDFS architecture to us, we have different data blocks or commodity servers. So those different data blocks or commodity servers have different data nodes that carries data on them. So those processors will work on their own portion of data. So let's say I make a select statement. Let's say I make a select statement that says select employees from HR table. So the different data nodes now, I don't use data nodes. So the different processors now will work on the data nodes, on the data tables that they are assigned to, and we make that select statement. They will carry out the operation of that select statement on their own portion of data, then produce a result. So when the different processors now have produced a result, your MapReduce now does something called shuffling and sorting. It will now sort out the different outputs and the different results of those processors. It will sort it properly into a defined manner. Then it will now serve it as an input into your reduce algorithm. You need to take note of this. I'm explaining the main process of your MapReduce. We call it MapReduce, but in actual sense, the real process or the real operation is map, shuffle and sort, then reduce. So you need to take note of it. So there's something that wasn't put in the name MapReduce. There's a shuffle and sort, or there's a classification or categorization of the different outputs gotten from the map algorithm. So the map algorithm has carried out its own operation and it has produced those outputs. So those outputs, it will shuffle and sort it. Then it will now pass it as inputs into the reduce algorithm. So it is that reduce algorithm that will now aggregate those inputs to give you your final answer, your final state, your final result. It's just like when you guys did SQL this morning and you make a select statement on a table. Then at the end of the select statement, you put your order by statement. Even after your order by statement, you now put your group by statement. Let's say group by age, group by class, group by anything you want to group by. So it's like your reduce algorithm is working more or less like a group by statement or an order by statement that aggregates your data results, aggregates it into a well-defined format for you as a final result. Okay, so going from the slides here, okay, don't let me too fast here. Going from the slides, I've already explained everything you can see on the slides. Yeah, okay, I've already explained all this. Okay, so now I'm going to go to, please, if I'm moving too fast, you can always let me know. And if you have a question, you can always raise up your hand also. Okay, so now let's look at the characteristics of MapReduce. So like I tell you guys, if you are going through maybe your data science school platform, always take note of the points highlighted in, okay, let me say light green or gray. Yeah. So the important characteristics of MapReduce, please take note of this. I'm talking about the general functionalities of MapReduce as regards to the original Hadoop ecosystem. So some of all these functionalities now, it is being shared with the yarn, but yet this is what the MapReduce compute engine is capable of doing. You still need to take note of it. So the very first one now is scheduling. The first characteristics of your MapReduce is scheduling. Just like I told you, it breaks jobs into individual tasks for the map and the reduce portions of the application. Then the next thing is synchronization, making different multiple processes to run concurrently. Then you have what? Your code or data collocation. So what that one means is that your code and your data exist in the same memory, in the same domain, within the same region. Then the next thing also is, the next characteristics of your MapReduce is your fault or error handling. And if you notice from the last class, I told you guys about the issue of single point of failure. Single point of failure means whereby you have a certain how do I put it? Okay, you have a certain entity in your Hadoop ecosystem now. Let's say you have just one copy of a device, one copy of a file running in your ecosystem. Then when that device fails or breaks down now, you don't have any other device to come or work in place of that device that has broken down. That's what you refer to as single point of failure. But with your MapReduce, you're able to avoid that because it would provide different nodes. It would, just like I told you, to replicate itself in different nodes, in different commodity servers, in different data blocks. That way it is able to handle error and fault, is able to handle error, and in case of fault, you should know that yes, you are covered. It's definitely going to go to its standby replica device. So if one process or something should stop, it will be able to rerun that process again with another device or another node. Okay. So, okay, yeah, the first knowledge check now. If you guys don't ask questions, I will be the one asking questions then. So the first knowledge check now. So discuss how you can create a business data analysis stacks and apply MapReduce to it. So the first option is, okay, the first one is describe the business situation you have created, the data to be analyzed, and the question you want to be answered. Describe how the mapping function will work in the process. Describe how the reduce function will work in the process. Explain the advantages of MapReduce compared to earlier systems. Okay, can anyone help us with any of the questions? Someone should just describe a business situation. Someone should create one for us. Then the data to be analyzed, the questions we want to answer like that. I'm going to call names.
Yeah, so can you hear me?
Yeah, I can hear you.
This is Hubert. My network was really horrible during the last class, so I want to contribute to this. So any correction will also help me to understand better.
Okay, no problem.
Okay.
Go on.
So I'll create a business problem now. Okay, let's say I really don't know how this works, so I'm just trying to be as abstract as possible. So probably MTN is looking for how many to judge based on I always give you this example, I don't know why. MTN wants to know how many people are using 1 GB plan in each state in Nigeria. Okay, so we probably have different nodes or specific processors that would be handling each state. But imagine that we're using the parallel computing here where we have the single memory. So we have
Okay.
we have the 36 we have 36 processors and then one memory. So 37 including the SCT. So now in this case we'll have the names and IDs of each client or
Customer.
subscriber or customer. We also have
Yeah.
the location. So there's the location that's being looked out for, and the number and the phone numbers and the subscription that they usually go for. So the map reduce function in this case would help to after each processor has been able to collect this data. I don't know if that's how it works. Once this processor has collected and completed their data, the map reduce is now going to come in to collect all the data together and put them into a single memory to have a single, let's say, a single file that has all the data that's needed for also all 1 GB subscribers on MTN in Nigeria from L36 states. Now, the map, the error, is there an error for correction? No, there's no error part here. Anyway, there was a part where it talked about it correcting errors. So probably if somebody's code was wrong or somebody's location was, collected, or somebody was using the VPN and its IP address was changed at some point, and something. So the map reduce is going to help to reduce that error of that kind. So, yeah, Eddie, I'd like you to correct me any error I've made right now. I just wanted to do this.
Okay. No problem. Nice one, Ubert. Like, nice try. Like, that's awesome. You tried. You did great. That's very good. Okay, so I'm going to pick up your business situation, your business problem now, then answer this question. So your business situation is, okay, we are data scientists that work with MTN Nigeria. So the data to be analyzed is, we have data concerning the consumption rates, and demographics of our customers in Nigeria. So when we talk about demographics, meaning we have the different state locations of these customers. Then for consumption rates, we have how much they subscribe per month, per year, like that. So now the question you want us to answer is, we want to know those customers that consume at least 1 GB of data per month. Am I right? Did I get your business situation?
Yes, you did.
Okay, awesome. So now the second question there says that, okay, in that type of real life scenario now, how would the map function work in processing? So the map function in this real life scenario, what it will do is, so definitely we pass our data into the map reduce compute engine. So the map function definitely, just like you said, can create 36 processors that are sharing one memory. So what it would now do is it will now pass out the different data in different batches based on the location wherever those customers are in Nigeria. Meaning customers in Lagos State can be apportioned to one processor. Customers in Abuja FCT, one processor. Customers in, let's say, Cross River, one processor, like that. So like that, we have 36 processors. So just to correct you based on an error you made earlier, MapReduce doesn't, let me state this clearly, MapReduce doesn't correct error on your data, on the information. The error, the fault handling that MapReduce does is that if in the process of running this operation, of running that task, maybe one of your processor fails, it wouldn't give you an output yet until another processor has been assigned to carry out that task that the previous processor failed on. So meaning that one, anyone that is on standby, meaning any replica that can be gotten within the HDFS cluster, any extra node or replica that can be gotten will be used to run that task or process. So it's like what I meant by fault tolerance or error handling is, in case any of your memory or processor fails, like there is a backup, there's a standby replica for it, ready to run that task. So how does the map function work now? So if you notice, the map function has scheduled the different, your HDFS normally, data has been separated into the different portions of the data nodes for different processors. So your map function now has mapped what each processor would do. That's the work of the map function. It has mapped what each processor would do. So when each processor has finished running the task, the map function will still run a shuffle and sort operation. So what that shuffle and sort operation means is that the information it has gotten from different processors, it will shuffle it and sort it in a predefined manner, then serve it as an input into the reduce function. I'm already talking about the third statement here now, which says describe how the reduce function will work in the processing. So what would the reduce function now do now? The reduce function will now collate all our responses and aggregate them into a final answer. So the final answer or the final system, just like you said now, can be it is either the total number of customers per state that use at least 1 gigabyte of data per month, or the details of those customers per state that use 1 gigabyte of data per month. So the reduce function is more or less like the aggregating function. After spreading it into different 36 processors, it will now aggregate everything together and give you your final output. So the last point here says, okay, explain the advantages of MapReduce compared to earlier systems. So one major advantage of MapReduce to earlier systems is that before, earlier systems now, to run this kind of operation now, it can take you hours to run, it can take you minutes, it can take you days to run. But because of the technology by which MapReduce run, which is either the distributed computing or the parallel computing, you're able to run operations and tasks like this very fast, like faster than before. So that's the major advantage of your MapReduce. And it is able to share your work across different processors. I hope you're able to get me. I don't know if that is clear enough.
Yeah,
You guys get me?
Yes.
Okay. Sorry. Can you please explain the advantage again? Oh.
Okay. So the major advantage of your MapReduce over earlier systems is that you're able to get your results faster. Because of what? Because of your distributed computing and your parallel computing technology. Another thing about your MapReduce is that in MapReduce, you can pass in your data just like that in any format, be it unstructured or structured or semi-structured. But some earlier systems before, you would need to wrangle that data to some certain format before you can pass it into MapReduce. But MapReduce can take care of the wrangling, cleaning, and everything. Just give it to it as it is. So those are advantages of using MapReduce to earlier systems.
Thank you very much, sir.
Thank you very much.
I
Please.
still don't understand the essence of shuffling.
Okay, so the essence of shuffling, I know right now it looks so ambiguous now, but I'm going to use a diagram very soon to explain that to you at the tour. Meaning, as we take more use cases, you would see the reason. Though it is not, in fact, funnily enough, there are some operations that you, in real life scenario, let me tell you, there are some operations that you pass into MapReduce that all you just need is just the mapping function. The reduce function is not even compulsory. That's the funny thing. Like the business scenario that Hubert gave to us now, we can say the reduce function is not necessary because the mapping function has already done the major thing, which is distributing the task over 36 processors created. So the reduce function is more or less, except if maybe the result we get to is like, okay, customer with customer ID 967, that's one customer. Customer with customer ID 444, that's another customer. So that's where the reduce function can now aggregate all of them together and say Lagos customers, put the number beside it. For Lagos customers, we have 46 people that are using 1 GB of data per month. So that's where the reduce function comes, meaning like we are trying to get the count. But there are some MapReduce operations that does not require the reduce functions. And for the shuffling and sorting, you would understand better when I show you an architecture that talks about MapReduce operation. Okay?
Yes, sir. I thought that. Sorry.
Okay, go on.
Yes, sir. I thought that the reduce without the reduce should I call it function now? You can't, more like that's the, I don't know how to call it. More like the mapping can help you probably analyze your problem, but then you can't really come to more like this the problem statement Hubert gave now. There was a question we're supposed to answer at the end of the analysis. So without the reduce function, we can't answer that question.
Yes, exactly. Without the reduce, and sometimes some questions will not even need you to get some operations will not need the reduce function. That's what I'm just trying to explain to you. Okay, I will try to get an example on that. Okay, let's just move on.
Please, can I ask a question?
Okay, go on.
Okay. Please, can you define what the question meant by other systems? In the knowledge check, it said the fourth question that the advantages of MapReduce to other systems. So what are those other systems that we are talking about?
So other systems that we are talking about replies to, okay, before the advent of MapReduce on Hadoop, okay, before the advent of Hadoop, normally people will just get their data, they have to clean it before passing it into maybe their computer or their relational database system before they can make sense of it. So if you are saying I should give an example of those other systems, probably you are saying, okay, your normal computer, you just pass it normally. So before the other systems it's referring to is maybe the ways of using database system, your RDBMS, to make sense of data, using maybe some other programming tools like the likes of C, Objective-C, C++, and the rest to try to make sense of data. That's what you can regard to as other systems. But thanks to Hadoop, MapReduce technology in Hadoop, we're able to handle big data these days. So that's what it meant by earlier systems. So earlier systems refers to computing. Yeah, different ways we're computing, handling big data before.
All right, sir. Thank you very much.
You're welcome. Okay. The flow diagram of how MapReduce works. You start with a large amount of data or number of records, iterate over the data. It uses the mapping function to extract something of interest and create an output list, then organize it, then it uses the reduce function to compute a set of results, then produce the output function. We've said all that. So, okay, continuation of how MapReduce work. Like I told you, it divides the task. It divides every task into, it divides it into two tasks, which is the map and the reduce. The map task works on part of the data in parallel, and each task returns an output. Then the reduce task will receive this output as input, then produce your final result. So to go into detail now, we are now going to talk about those components in MapReduce that make the MapReduce algorithm possible. Remember what I told you. In fact, these components that I'll be mentioning now, this was how the initial Hadoop 1 ecosystem, Hadoop 1.x ecosystem was created. So I'm going to be calling those components now. So the very first one now is your master node. Your master node, you can refer to it as your job tracker. So what does your master node do? So your master node, it is the responsibility of your master node to schedule different job tasks to, let's say, different processors for execution. Then, just like I told you guys about fault and error handling, it re-executes failed tasks. So any job that you scheduled that wasn't able to run properly, it will try to re-execute it. So that's the work of your master node. And if you remember in our last class, I told you guys about the name node and the data node. So it's like right now, the name node and the data node, that's what you have for your HDFS, your Hadoop distributed file system, when we're talking about the architecture of HDFS. But now, those two things that have the same relationship in HDFS in your MapReduce. For MapReduce, we have the master node and we have the slave node. So you can say for name node that you have in your HDFS, it is master node in MapReduce. Then your your data node that you have in your HDFS, it is slave node in MapReduce. But they all perform different functions. So your master node in MapReduce is your job tracker. It schedules different jobs, separates the jobs into for different processors to run. Then your slave node is your task tracker. So these ones are the ones that will actually run those tasks and produce an output that you now feed as input into your reduce function. So look at this diagram here now. With this diagram now, you'll be able to understand what I'm saying better now. So at the top of this diagram now, let's say this is the business situation that Ubet gave us, computing tax. So this computing tax now, this job has come down here now. So initially, it is not going to go into the reduce function. It will go first into the map function. So when it comes into the map function, so this is the first thing it encounters is the master node. The master node will now share the different jobs and schedule it into different slave nodes. So for this point now, this is the master node here. For Uber's problem statement, let's say it will create different 36 slave nodes. You get now. So for this particular statement, it has just 2 slave nodes. It has tax tracker 1, tax tracker 2. So for Uber's problem statement, you can have tax tracker 1 down to 36, like that. So it is now those ones that will now run the different jobs like that, then produce an output. Then this output is now being fed into the reduce function. Then the reduce function will now aggregate it and work on it, then pass out your final output. This is the normal and the ideal MapReduce syntax. But just like I told you, sometimes some problem statements might not necessarily require the reduce function. Probably, okay, when I'm able to get an example on that, I would share it with you guys. I'll share it with you guys. So going on, this one is just saying, okay, HDFS and MapReduce perform their work on nodes in a cluster hosted on racks of commodity servers. I already explained part of this in the last class. The following process explains how MapReduce performs its tasks. Wow, so much emphasis on how MapReduce works. Okay. So what does this flow diagram say again? It splits the input into multiple pieces of data. It creates master and workers. So it's meaning your master node and your slave nodes. Execute the worker processes remotely. Then different map tasks simultaneously work and read pieces of data. Then pass it as an input into the reduce function to work on every unique key. Then from the reduce function, it transfers the control of the user program. Then instruct the reduce workers to begin their work to produce the final result. Okay, yeah, exactly now. So Ade Toro, I hope I'll be able to answer your question here now.
Yes.
So look at this now. Can you guys see this? So if you can see, you have your map function here, right? So your map function, it schedules the job into different nodes, as you can see. So as it schedules the job into different nodes, so let me take Uber's problem statement now. So let's say we have the same data set, the same different data sets across the different nodes. So for that portion of data that this particular node has access to, it will produce the number of customers that consume at least 1 gig of data per month for the portion of data here. It will for different states. So for UBET, I would want to reiterate that, okay, so the ideal thing is that for the number of nodes available, it's not going to divide it according to the number of states. That was a mistake on our part. So it depends on your architecture. So it will split out your tasks based on the number of processes it has. So for this particular first node now, it will bring out the result for each state. So for each of the 36 states on this particular portion of the data here, it will bring out for Lagos State, for the different states, the number of customers that consume at least 1 gig of data. Then for this portion of the tax too, this one too will also do its own, this one too will also do its own, this one will also do its own. Then it is at this point that it now shuffles it and aggregates it into it is at this point it tries to shuffle it. So it tries to say, okay, let me pick out those ones, let's say Lagos State, Osun State, or your state and the rest. Let me pass everything to this particular node. Let me pass everything to this particular node. If not, it does shuffling and sorting. So what it does is it's trying to reduce the tax that the reduce function would have to work on. It's trying to sort it out. So the map function will try to sort out the results that you've gotten as output. Then it passes it into the reduce function. So let's say in this first node now, we have Lagos State, Osun State, Oyo State, and Ekiti State. So in this one now, we can have Kaduna, Kano, and some other northern states. In this one now, we can have southern states, let's say Rivers, Cross Rivers, and the rest. In this one now, we can have some other states also. If you notice, at this stage here, states are already being sorted. But at this stage here, states are not sorted. Map function is only performing its tasks on that portion of data here. So at this node here, you can have an instance of all the 36 states on this node. You can have two instances each of all the 36 states on this node. You can have multiple instances on this node. But by the time it's getting into the reduce function, it would have shuffled it and sorted it out in such a way that the reduce function can aggregate it easily. So by the time it's coming out of the reduce function, it should have aggregated everything properly. It would have summed it all up to produce your result. So for Marvelous that asked me about the advantage of the MapReduce over earlier system, MapReduce breaks your job into many pieces and runs them independently. So it runs them simultaneously, just like your batch processing. It breaks it into different sections, different columns, then runs it simultaneously. So this is a typical map reduce process. I don't know if I've been able to answer your question, Adetoro. Hope it is clear now.
Yes, it is. Thank you very much.
Okay. So, okay. So moving ahead. So this is just okay. Yes. Now, so imagine. Okay. Okay. This is an online customer service chat, for example. Now, so these guys now, instead of going through the normal process of NLP, natural language processing, whereby they have to do a lot of data wrangling, data cleaning, they have to do the count vector, count TFD, count vectorizer, they have to create bag of words and the rest like that. What these guys just did is that they just passed their data, their unstructured data or semi-structured data into MapReduce to make sense out of it, to do analytics on it. So instead of going through the whole long process of having to get your data ready for NLP, maybe to do sentiment analysis, for review analysis, for analysis on ratings and the rest. So they just pass their data like that, their chunk of text, into MapReduce. So what did MapReduce do? What did they do? First of all, it splitted the different words into different bags automatically. So it has splitted it into different nodes. So for this node now, we don't know the word that is on this node. We don't know the word that is on this. Okay. So what did you do? Okay, yes, we can see the word that is on this node. For this map now, we have words of my. So for all the data present in this node, it is checking for my. For all the data present, no, that's wrong. Okay, this is how it is. We don't know. Yeah, that's right. This is the chunk of word that they are looking for specifically. They are looking for my, they are looking for product, they are looking for broken bone, they are looking for broke, they are looking for broken, they are looking for angry, other words like that. So these are the words that they are looking for. So for the data available here in this node here, they will check for all these words. For the data available here, they will check for all these words. For the data available here, they will check for all these words. So for each of these different nodes now, it will now pass it out into the reduce function. But before passing it out into the reduce function, it will now shuffle it. So for this first shuffling now, this very first reduce node, this very first reduce node is looking for the word called my. Then the second reduce node is looking for the word called product. Then this third reduce node is looking for the word called broken. If you notice, after it passes through all this reduce function, which is this reduce nodes, if you notice, it says in this data set, in this chunk of words that we've passed to, we have 10 instances of the word called my. In this chunk of ratings that we've passed to, we have 25 instances of the word called product. In this chunk of words that we've passed to for this reduced node, we have 10 instances of the word called broke. So you can see that's just basically how it works. So this is where you can see how the shuffling and sorting happens. It checks for every word in each portion of data available in that HDFS. Check. Then it shuffles it and sorts it out based on the operation, the major question, and divide it into the different reduced nodes to give you different and to give you the different answers. So more about map and reduce functions. Okay. So if you notice from what I showed you guys here, actually from what I show you guys here, you can say these are key value pairs. So what I mean by key value pairs, meaning you have a target, then you have a key to it like that. So now the target here is my. So what's the result for it? 10. So it's key value pairs, meaning matching for every of your targets, it is giving you values for it. So that's one thing that MapReduce does. So here now the target was product, then the value given for it was 25, meaning we have 25 instances of products out of all the reviews or the data set submitted into the MapReduce compute engine. So just like I said, okay, this also in this box here, it tells us how the MapReduce function work, especially the map function. So the map function extracts characteristics of interest and present them in key value pairs format. Then map gain, so just telling us how the map function gained popularity in the world of AI. In the world of AI, through a language called list processing. That was where the map function gained popularity from. Okay, so MapReduce works with Hadoop and natively uses the same language. MapReduce function can be written in Java because Hadoop is written in Java, so you might want to take note of that. The MapReduce framework uses key value pairs as input and output. For those of us who are programmed in, let's say, Python now, I'm sure you know the dictionary data structure, whereby for every key you have a value. So that's one concept, or that's the data structure MapReduce works with. So for this now, we are looking for the my keyword here now. So out of all the data sets here, out of the portion of data here, it will try to count for each instances. Like now you can see maybe the first row now, you have my there, it will say my 1. The second row now, we don't have my there, it will say my comma 0, my comma 0. So at the end of everything, it will now sum up the answers, the values of all the instances of my in this portion, in all the portion of the data. So when it summed it up, that's when we got 10. When it summed it up, that's when we got 25 for product. So that's just basically how it works. Key value pairs means for every target you are looking for, there is a value for it. Okay. So now this is also another example of another real life scenario of using the MapReduce function. So let's say we want to create a program now that counts the number of counties in the United States having population greater than 50,000. Okay, so let me try to rephrase this question so it wouldn't get us confused. Okay, so let's say we are trying to create a program that counts the number of people in, okay, let me put it this way. We are trying to create a program that counts the number of counties. Let me take it just the way it is. The number of counties in the United States having a population greater than 50,000. So to do this, what would we do? The very first thing we'll do is we would identify the input data and create a list. So the very first list we'll do is, assume this is not a programming language, this is just normal thought process, your normal pseudocode. So all counties in the US that participated in the most recent general election. So let's refer to counties as eligible voters, as voters that participated in the US in the most general election. So we have a data set that contains all the voters that participated in the last election in the US. So that is our data set. That is the list we have. So the very second step we'll do is we'll create a function that will select voters in each state with more than 50,000 people. Do we get that? So we are creating a function. That function is going to select voters from each state. Every state that has a population of more than 50,000 people, we are going to create a function that will select voters from that state. That will select voters from such states that have people more than 50,000 people. So what would our mapping function do now? Our mapping function will work on the list. The very first thing it will do is how many people. So what does that mean? Meaning for each state, for each, sorry, please excuse me, I'm coming around to pick a call. Yeah, thank you. So Okay, so for each state, it's okay. Where are those states that we have at least 50,000 people in the United States? That's the very first thing. So the very first thing it will do is, okay, let's count how many people are eligible voters first per state. So what it will do is, okay, let's say county one, how many people do we have? Then after counting the number of eligible voters we have per state, so the second thing it will now do is, so we have counted the number of eligible voters per state. We have that answer already. So the second condition is, since we know the number of eligible voters per state, now we want to know those states that have population more than 50,000. Then identify the number of eligible voters that they have in those states. So that's when you have something like this now. So for this first entry now that is separated by a semicolon now, so this very first state now, we have a total number of eligible voters numbered at 1. So the number of eligible voters we have in this state now is 1. Let's just assume is 1. Then the no here refers to, is, does this state have a population greater than 50,000? No. So we go to our second, oh sorry, don't mind me. So this is the key and this is the value. This no refers to the number. Wait, sorry. Oh, okay. So we have the number of eligible voters counted as 1. So does this state have a population of more than 50,000? No. So we go to the next one now. So for this second state now, we have a total number of eligible voters. We have two. Two is the total number of eligible voters. Does this state have a population greater than 50,000? Yes. So we go to the next one now. Total number of eligible voters is 3. Does this state have a population of more than 50,000? No. So we go to the next one now. Total number of eligible voters is 4. Does this state have a population of more than 50,000? Yes. So on and on like that. So that's how it does it for this problem. Okay, these are different knowledge checks. Wow, we are far behind schedule, so I wouldn't be able to go through them, but we can still come back to them. So that's it on MapReduce. We still have Yarn and we still have HPs and we still have Hive to look at this afternoon. Sorry, I'm take like 3 minutes break. I'll be with you guys soon. thank you. I hope you are all here. Okay. Okay, so now we want to talk about optimization techniques in MapReduce jobs. Okay, so when we run our MapReduce jobs, what are the optimization techniques that MapReduce does? So the very first thing it does is, okay, let's look at in the aspect of hardware or network topology. What does MapReduce does? So MapReduce tries to keep the commodity hardware within a rank. Okay, it keeps the data and code together, just like I told us before. Code and data collocation. Then synchronization, it copies the mapping results to the reducing nodes immediately after they have been completed. So meaning it sends all values from the same key to the same reducer, which is the reduced node. Then file system also, it creates a standby, which as well, it creates a standby master node for possible online master failure. So this is one of the things it does in the place of fault or error handling. One of the things it does to avoid single point of failure, just like I have explained before. Yeah. So applications of MapReduce. So we can use MapReduce. Maybe we have web page visit analysis to do, or we have web page visitors parts to do, what frequency. So in terms of web page visits, so let's say right now we are trying to read the log of our website. So what we are trying to do is, let's say we want to know the number of, okay, let's say we have researchers now that they want to know the number of times website of a particular newspaper was accessed. So we want to know how many times they accessed a particular website. So the mapping task here will be to read the logs of the web page and make a complete list. Then the reduce function will be find the results of the newspaper URL and add them. So that way it will add all the values for which the newspaper URL was clicked, then add it and give you the value. That the value will be the number of times people accessed that newspaper URL. It will be the number of times people clicked on that newspaper URL on the researcher's website. So you have web page visitors part. So let's say an advocacy group wants to know from what web pages people accessed their website. So one thing they can do is, so the mapping function here, what would it do? The mapping function here will scan for the key, which is the target, then the value. So the value here will be the source, meaning from which website did you access our page. Then the reduce function here would be, it will scan the list, then select the result where the target is equal to the advocacy group. So meaning from the data provided, it will select the result where the value is equal to the advocacy group's website. So meaning they will pass in data containing different, they will pass in data that contains different visits to different websites, meaning the website, the different internet log for that company. But those people that access the website of the advocacy group, that's what the reduce function will try to reduce. We try to aggregate and count. So what frequency, just like what I told you, just like the example we saw in the MapReduce flow process, in the MapReduce operation example that was shown to us, counting the number of words we have in a chunk of text or data sets. So let's say researchers want to find out about earthquakes, like that. So it will count the number of words. These are applications of MapReduce. Okay. Wow. So finally, I would say we are done with MapReduce now. We are going to Yarn. So just like I told you guys, before you can talk about Yarn, it means you are referring to the Hadoop 2 ecosystem. In Hadoop 1 ecosystem, there was no Yarn. It was just purely HDFS and MapReduce. But because with the MapReduce, they couldn't really, MapReduce wasn't optimizing the full functionalities of the Hadoop ecosystem, of all the components of the Hadoop ecosystem. Like, we couldn't utilize it properly. That was why Yarn was created in Hadoop 2. So looking at this now, I want you guys to look at this very first statement. So MapReduce continues to be a successful programming language, but in Hadoop 1, the task scheduling capabilities for parallel execution of MapReduce applications, and typically only one batch job could be executed at a time. So meaning, just like the problem statement and Hubert helped us with now. So meaning in Hadoop 1, we could only focus on Hubert's problem statement. But with the advent of Yarn, with the creation of Yarn in Hadoop 2, so meaning as we are running a process, or as we are running a task, or as we are executing a batch job on Hubert's problem statement, we can also be querying the same data source from another front-end application simultaneously, or we can also be running another job also in background for maybe a Butaminous problem statement, or Torus problem statement, or Richard's problem statement. So look at this now. In Hadoop 1, resource allocation was static. So meaning you wouldn't know what processors or what nodes are available because MapReduce was the only one doing everything. But in Hadoop 2, Yarn provides Hadoop with a more efficient and flexible workload scheduling and resource management facility, which helps Hadoop to run more than one MapReduce jobs. So meaning with the presence of Yarn now, you can run more than one MapReduce jobs. But in Hadoop 1, you couldn't. You could only run one at a time. And if you can remember from the last class when I was explaining and when I was teaching us on understanding the Hadoop ecosystem, I made us understand that the major administrator, the thing that manages the processes of the HDFS and the MapReduce compute engine, is the Yarn. So the Yarn is more or less like the administrator that coordinates most of those things. So how does the Yarn do this? It does this through resource management, global resource management that I explained to us, through the resource manager and the application and per application management through the application master or manager. So I'm going to be explaining that in detail now. So how does Yarn and Hadoop 2 affect our analytics? So the new feature provided by Yarn increases Hadoop analytical capabilities greatly. So with Hadoop 2 now, we can do real-time analytics, we can do batch analysis, and we can do interactive data in much more easier way and simultaneously than before. So with Hadoop 2, the Yarn has already decoupled the resource management and scheduling capabilities from data processing components in Hadoop, meaning the Yarn has relieved the MapReduce of some of those headache it was bearing before, which is maybe I have an operation now. So MapReduce has to be the one to divide that operation into many tasks to different nodes or processes available and still run its map function on the data again. Like after doing scheduling, it will still run its own map function. It's like MapReduce is doing more work. So with the advent of Yarn now, Yarn has lifted up that burden from MapReduce and has taken over the resource management and application, and it has taken over the resource management in your Hadoop ecosystem. It has taken it away from MapReduce. So meaning the one whereby almost everything that, like now in your Hadoop 1 ecosystem, before you can do anything, everything you try to do, it depends on the MapReduce. But now you don't necessarily need, like, all the old stress and the burden has been lifted off MapReduce. So in Hadoop 2, one thing you need to know is each application is controlled by its own application master, and that application master is under your Yarn. If you notice, your Yarn application master, from the name application master, resource manager, so he's the one that controls everything. So what does the application master do? So let's say an application needs some set of resources now to run. So the application master will submit the request that, oh, I need like 2 nodes of processors to run my job. So the application master will submit a request to the resource manager, So the resource manager is also in the yarn. It's now the resource manager that will now check, okay, let's check, do we have 2 processing nodes available on standby that are not doing anything? If it is available, it will make those nodes available for that application to be able to run. So it does all the whole job tracking and scheduling and everything. So Hadoop 2 goes beyond HDFS and MapReduce for distributed computing and large-scale data processing. Wow. If you don't, let me know if you have any question. If you don't understand, okay. So now let's go to storing big data with HBase. Though I already explained what HBase is to us when we're taking the last class, and I also gave a brief. Okay, sorry, give me some minutes. Okay, so I already explained to us what HBase is to us in the last class and what it does. So I'll just go through over it again just to add to it. So HBase is an open source, non-relational distributed database. Okay, it is column-based. It has column-based compression and storage, meaning you can compress the columns in HBase. There's no the one that permits table partitioning and data bucketization is your Hive. HBase doesn't permit that, but HBase permits compression of data in terms of compressing the columns, just like your normal RDBMS, but it's quite different. Then with HBase, you can update efficiently. You can also make requests to your data in real time. So the reason why HBase was created was for those people that maybe they want to work with streaming data and they need real-time analytics to be performed on that data. So you can use HBase to work on large data sets. You can use HBase to work on streaming data that is coming at a very high velocity. So that's one of the reasons why HBase was created, just to create something that can accommodate people's in terms of volume, it can work well. In terms of velocity at which the data is coming into the data and the data bank, it can also accommodate it. Then in terms of getting responses for queries also, it can also accommodate it. So that was why HBase was created. As we can see, it says HBase is useful when large amount of information needs to be stored, updated, and processed even at a high speed. Then it's telling us the different types of data HBase can store. HBase can store database, can store demographic data. It can store GPS data, different lookups table data. It can store almost any type of data also. Then it can also receive log or streaming data and update the database fast enough to allow processing. So if you want to work on large data sets, yes, large data set and at a very fast rate, you can use HBase. So one other additional thing I can add to you guys is HBase work for those of us that have used cloud technologies. HBase is similar to your Google Bigtable. Yeah, it's similar to your Google Bigtable. Then in Azure, I think HBase is similar to your Azure Databricks. Yeah, Azure Databricks. So, okay, what else? So your HBase runs on your HDFS. It's more or less like a component that interacts directly with your HDFS. Okay, these are just some extra information if you wish to know. So to run HBase, you need your Amazon Enterprise MapReduce cluster. Your EMR means Enterprise MapReduce. EMR means Enterprise MapReduce. So it's just telling us if you want to set up HBase in real life scenario, what are the prerequisites to setting it up, the things you need. Okay, it says your EMR cluster should meet the following requirements. So meaning in your Amazon Cloud Console, your AWS console, as probably the root user or an IAM user, your HBase should run on persistent clusters. So what it means by persistent clusters means the kind of storage disks you add to your AWS EC2 instance should be persistent disks and not, let's say, your SSDs or your HDDs. So your persistent disk. So one thing I know persistent disk is that is basically maybe you want to store data. You want to store data that allows for high scalability, meaning you don't know the exact size, but it should be able to handle whatever data that comes into it. You should be able to hold it for a specific amount of time. So you can create your enterprise map reduce cluster using your Amazon CLI, your command line interface, or from your EMR console on AWS. Okay. Then it also tells us different prerequisites. Okay, your EC2 key pair must be set at the time of creating the HBase cluster. This is basically for people that are interested in. We are all interested in it. At some point, you would maybe want to set this up. If you are a technical person or you choose to be a data engineer, you might need to set this someday. Okay, so these are just the major requirements if you need to set up your HBase. So the focus here is with Amazon technology. So maybe the company you work with later in future might be using Microsoft, then you will have to look at setting up HBase with your Azure Databricks and the rest. Or if it's not Microsoft, then let's say it's with Google, then you might look at setting up your HBase in Google Cloud with your Google Bigtable. Okay, so now we are getting close to the end of the class. So now we are talking of mining big data with Hive. So like I already told us from the last class, Hive is a data warehouse built on Hadoop. Yeah, Hive is a data warehouse that was built on Hadoop. So okay, it's the one that gives you Hive is the one that works on the structured part of data in your Hadoop ecosystem. So it works more or less like your normal RDBMS, which is your relational database management system, like your normal RDBMS tables. Then, like I told you, it permits table partitioning. Then it permits bucketization of data on the file system. Then with your Hive, you can run processes using your SQL-like queries through the implementation of your HiveQL. Then, as you can see, HiveQL offers most types of SQL processing, such as your select, aggregate, union. Some of those SQL-like queries you guys would have played with today in the morning. Your Hive permits that. Then, MapReduce works on mostly your structured and semi-structured data. So with your HiveQL, you can work on the structured part of your data, and it permits you using SQL for querying and aggregation and getting results from your data. So basically, you use your HiveQL for your data mining and deep analytics. So what do they mean by deep analytics? So deep analytics maybe means you want to do a deep dive into what's causing a part, meaning you want to do a deep dive into answering some business analytics questions. I'm sure you guys would have heard of deep dive 101, deep dive 102. So what deep dive means is that you are digging deep into, okay, what can be the root cause of this major issue? So it's more or less like a business intelligence whereby you are committing, like you want to take every instance of that data, every possible condition possible, want to check everything, want to be able to answer questions. So it involves maybe you writing queries and sub-queries just to be able to get answers to some very, very funny questions. Yeah, like maybe, let's say you're doing, no, let me go too far on that. Okay. So what else? Other processing patterns that we have in the Hadoop ecosystem. So you have your interactive SQL. And what does your interactive SQL mean? So your interactive SQL means, let's say you don't want to use Hive now to work on the structured part of your data. So with more new technologies like your Impala and your Tez now, you can be able to write SQL queries on Hadoop and still be able to scale up on large data sets. Then iterative processing, what does it mean? It means sorry. So iterative processing means algorithms or processes that are iterative in nature, like let's say your machine learning algorithms, whereby you try to build a predictive model for maybe predicting churn rate or predicting loans that are performing or non-performing, or maybe predicting house prices or something, maybe be it a regression task or a classification task. So all those processes like that, especially machine learning process that involves iteration, lots and lots of iteration, you can now perform it now on your Hadoop ecosystem using a technology called Spark. Yeah, and it allows you to be able to it permits for high exploratory style on your large data sets also. So you also have stream processing. So what does stream processing means? Stream processing means you are running real-time distributed computations on unbounded streams of data with streaming systems such as, okay, let's say you have your Storm, you have your Spark streaming, and you have your Samza. So this can work by supplying results to Hadoop storage or external system. Like I said, you want to run real-time analytics on large data sets that is entering at a very high velocity. Let's say normally I'll be of the opinion that you can use HBase for that, but for people that are not comfortable with Java, you might want to use Storm or Spark streaming or Samza to work on that. Then you also have your search, as you can see. Let me just read this out here. It says, it is however important to know that various processing frameworks on Hadoop have been introduced over time. So map, okay. Oh, that's not even the definition of search. So for search, what search basically means is that you have data on your Hadoop ecosystem, then you are able to index it as a result of technologies provided, technology like your SOLR. So that one is added to your HDFS. You know, it's your HDFS that majorly houses your data in your Hadoop ecosystem. So as you're housing that data in your Hadoop ecosystem, you are indexing all these files and documents so that in case you try to search for it, it gives you a fast response and doesn't take so much time to give you a result. Okay. Okay, knowledge check. Let me check if we have time to take one more knowledge check. Okay. Then the next set of things, okay, point for you guys to remember. Points for you to remember. So the major points you guys need to remember is okay, MapReduce is a software framework that enables developers to write programs that can process massive amount of unstructured data in parallel across a distributed group of processors. You know, your batch processing. So MapReduce is a software framework that makes that possible. Then what I told you guys today, MapReduce divides your tasks into two major tasks. You have your map task and your reduce task. So I told you what your map task is. Map task works on part of the data in parallel and returns an output. Then reduce task, it works on the output of your map task, then aggregate it to produce your final result. Then I also told you that the MapReduce work using the MapReduce framework uses KVP, key value pairs, as input and output, meaning for every target you have a value for it, or for every key you have a value for it. Okay, then we also talk about different phases in MapReduce. So the very first phase is determine the exact data sets to be processed from the data blocks in your HDFS. Then you run the specified algorithm against each record in the data set until all records are processed. So that means for every portion of the data in your HDFS data node, you run your algorithm on every portion of the data in your HDFS data node. Then you locally perform an interim reduction, meaning you aggregate the outputs from your map algorithm. Like I said, remember when I was telling you this, that the reduce function is optional. So as you can see here, Adetory says this phase is optional because in some cases it isn't desirable. Hopefully I'll be able to get you an example, but right now I don't think I can. Then based on portioning requirements, group the applicable partitions of data from each mapper's result set, boil down the results to give you a single result set, which is the reduced part. Then we also talked about YARN. So what's the meaning of yarn? Yarn means yet another response negotiator. So meaning, why did we call yarn yet another response negotiator? The major thing on yarn is if an application wants to run in your Hadoop 2 ecosystem, remember what I said, yarn is only available in Hadoop 2. In the original Hadoop, it came with just your HDFS and your MapReduce. But because the tax and the whole Hadoop, the component of your Hadoop ecosystem was not being utilized properly. That was why we introduced Yarn in Hadoop 2. So basically, Yarn contains your resource manager, which you use for resource management. It contains your application master, which you use for application management. So why do we call it yet another response negotiator? We call it yet another response negotiator. Let's say we have an application now in our Hadoop ecosystem that wants to run now. So that application will communicate with its application master that, okay, we want to run so process, but okay, right now we need, let's say, like 2 name nodes, or let's say we need 2 processing nodes to run these tasks for this application to start running. So the application master will now communicate with the resource manager in Yarn that, okay, do we have any 2 possible nodes available for this application to run? Then the resource manager, which stores metadata of everything that happens in the Hadoop ecosystem, restores metadata about the HDFS, about the MapReduce, so it knows which nodes that are available and not available. So if it notices that there are some idle nodes on standby that are not doing anything, it allocates these nodes to that. It informs the application master that, okay, yes, so this application can run using these nodes for its processes. Okay, I already explained all this. Yeah, I already explained this. Using the location data, okay, yeah. Okay. Then I also gave examples of applications of MapReduce, like counting the number of visitors to a website or page. Then I also spoke about the advocacy group, which was listing the paths to a website or page. Then identifying frequently used words in a document. We saw that in the example that was explaining the MapReduce process, whereby they were trying to back some words. Then I also spoke about HBase, telling us HBase is an open source, non-relational, distributed database that stores, updates, and processes large amount of data at high speed. Let's take note of that. Large amount of data at high speed. I remember I also told us that if you also want to work with large amount of data and high speed, at high speed, funny enough, HBase is like your normal database system, your normal DBMS, because it stores data in a columnar manner. It is a column-based database system. But let's say your data is not in a column-based manner now, and you still want to process the huge sum of data at a high speed. That's when I told you guys about the processing partner that we refer to as stream processing. So to run stream processing, you need technologies, you need streaming systems like your Storm, your Spark streaming, and your Samza. Oh, okay. It's already characteristics of your HBase component. It has column-based storage and gives fast access to data for processing and updates. It stores data in memory and has low latency. Then, because of fast updates, the updated database is available for process immediately. Then it can handle data both slowly and in a very fast manner. Okay. Then we also talked about Hive. Yeah, I made us to know that Hive is a data warehouse that we use in processing structured data. I made us know that Hive is a data warehouse that we use in processing structured data, and we can run our SQL-like queries because we have an implementation of Hive that we can use SQL to communicate with, which is your HiveQL. So it organizes data in your normal RDBMS format. Oh, I already told us now. And Hive also offers your SQL-like queries, which is your select statement, your aggregate statement, union statement, and the rest. Then I made us understand that Hive is the best for data mining activities and for deep analytics. Although Hive is not designed for rapid responses or real-time analytics, the one that is designed for rapid responses and real-time analytics is our HBase. So other technologies that you might want to take note of for using other technologies that you might want to take note of for running SQL-like queries in your Hadoop ecosystem includes, you can use Impala or you can use Tez. By Impala, I mean IMPALA, or you can also use Tez also. Yeah, wow. So we have gotten to this part. So any question? Any question? Not, I'm going to ask questions.
Mr. Ademola, thanks so much for the lecture.
Okay, thank you, Richard.
But I didn't really get the concept of KVP. That was key value pair. Can you please explain it better?
You didn't really get the concept of
KVP.
KVP.
The KVP. Yeah.
Oh, KVP. That's your key value pairs. Okay.
Yes.
I wish there was a board I could explain that properly to you, but I'm just going to look for somewhere that talks about it in the slide and try to explain it. If there was a board now, I would have. Okay, exactly. There's an example for KVP. Yeah. I guess I'll just use this knowledge check to explain KVP to you guys. Okay, so let's look at this knowledge check now. Can you all see my screen? Let me confirm.
Yes, I can see your screen.
So, Mr. Smith recorded temperature of 4 cities over 5 months of period in 5 different files. So we need to take note of the conditions. Mr. Smith recorded temperature of 4 cities over 5 months of period in 5 different files. So we have 5 different files. We have CSV1, CSV2, CSV3, CSV4, CSV5. So he recorded the temperature of 4 cities over 5 months in those 5 different files. Each file contains record of 1 month. So for each month we have CSV. So for month 1 we have CSV1, for month 2 we have CSV2, for month 3 down to 5 we have CSV5. So each file has 2 columns to represent the names of cities and their corresponding temperatures. Can you get the key value pair here now? Richard, let me take it again. Each file has 2 columns to represent the names of cities and their corresponding temperature. So let's say for the city of Lagos now, we have the temperature of, let's say, 27 degrees. For the city of Benin now, we have the temperature of, let's say, 31 degrees, like that. So in terms of HDFS, that's your Hadoop distributed file system, these columns represent key and value pairs. Can you see, Richard? So in terms of HDFS now, this column represents key and value pairs. So what is our key here now? Our key here now refers to the city, and our value here refers to the temperature recorded in degrees. So as you can see, okay, going further, it says where key represents name of the city and value represents corresponding temperature. So now it's now saying from the collected data, from this data that we have collected, you have to find the maximum temperature of each city. So remember what I said, normally your reduce function will aggregate everything, meaning to sum everything up. Okay, well, I've already said the answer concept. With the help of the map reduce framework, you can divide the whole task into 5 smaller map tasks. Do you get now, Richard? So with the help of map reduce framework, we are dividing this major tasks into smaller 5 map tasks. So meaning we are having recording for each month. So since we have 5 months, we are dividing it into 5 smaller map tags. So let's say we are giving it to 5 different nodes, 5 different map nodes to work on it. So each map task works on a single file. So that means a particular node, remember what I told you, every node works on its own portion of data. Every node 2 will work on its own portion of data in your HDFS. Node 3 will work on its own portion of data in your HDFS. So now node 1 here in this case will work on the portion of data for month 1. Node 2 here will work on the portion of data for month 2. Node 3 down to node 5, where node 5 will work on the portion of data for month 5. So meaning you have node 1 working on the CSV file 1, you have node 2 working on the CSV file 2, then you have node 5 working down like that. So it's not saying with the help of the MapReduce framework, you can divide the whole task into 5 smaller tasks. Each map task works on a single file and provides the maximum temperature for each city in that file. So that means in our first CSV file, in our CSV file 1, for all the recordings now, let's say we have Lagos State at different points, different recordings. So let's say we have 10 entries of Lagos State, and let's say we have 27 degree recorded for each. So for those 10 entries of Lagos State, the total recording will be 270 degrees recorded for it. That will be the value for Lagos State, like all together, summing it up for an example. So the results produced by a mapper task is as follows. So meaning just for one mapper task that worked on one file, meaning on a certain CSV file, meaning on the data of 1 month, we have the following result. Okay. Okay. So this is it now. For city 1 now, on the first file for city 1, the aggregate the mapped function returned an output of 28 degrees centigrade. For city 2 now, so Richard, one thing I want you to look at here is the key here now is city 2. The value here is 16, which is the value. So that's why we have key value pairs, meaning for every key in the data set, for every instance in the data set, we have a value for it. So in the first CSV file now, for the entry of city 4, for the key of city 4 in the data set, the value we have for it is 19. Okay, I'm going to use this to ask question now. So okay, let me ask someone that has not spoken today. Daniel, are you with us? Hello, Daniel, are you with us? Hello, Daniel. Okay, Daniel is not with us. Okay.
Daniel has been having network issues. Sorry, Daniel has been having network issues today.
Oh, okay, no problem. Okay. Toby, can you help us with this question? So, for the third CSV file, what is the value for city 3? Meaning in the 3rd month, what is the value given to city 3? Is Toby here? Is Toby here? Toby, Oluwatobi Adeniji. Okay, Toby is also not here. Okay. Then let me just ask the person that asked the question. So, Richard, what's the value for city 3 in the 3rd month? Meaning in the 3rd CSV file?
That should be 20.
Yeah, very correct. The answer is 20 because this is the mapped output for city 1, which is month 1, month 2, month 3. So the 3rd city, which is city 3, the value is 20. Okay, so we have all these as the mapped outputs now. So the question says now all 5 outputs produced by 5 mapper tasks have been provided as inputs to a simple reduced task for finding a single value to each city, what will be the final output? Sunday, can you help us with that? What will be the final output that will be produced by the reduced function? Sunday Ogunleye, are you with us?
Hello.
Yes, so I want you to give me the final result that will be produced by the reduced task for city 1 and 2.
I can't get your question, sorry.
Okay, I said now we have all these 5 outputs by our 5 mapper tasks. So for the reduced task now, for the simple reduced task for finding a single value of temperature to each city, let's say temperature to each city, what will be the final output? I remember I told you reduce function, basically what it just does is it aggregates. Yeah. Aggregates the value for a particular key. Can anyone help with that? It's quite simple. I already
City
said the
1.
answer. Eh?
City 1.
And city 1. Okay, for city 1, what's your answer?
Okay, it's going to be 28 and 21 for city 1 and city 2, since we're getting the maximum temperatures.
Okay, 28 and 21, since we are getting the maximum temperatures.
I have a question, sir.
Does any other person want to answer this?
Sorry, excuse me.
Okay, go on.
Yeah, I think you mentioned that it is going to carry out the sum for each of
Yes,
them.
exactly.
So
That's the right answer. It is not going to be
first,
28. It will just sum everything out. So I don't make the mistake here. Sunday, I know definitely you'll be like, okay, temperature, yeah, we can't add temperatures just like that. It makes no sense scientifically. But this is just, let's just assume we're just following the normal map reduce process. So when you gave your answer, I told me 28, since it's going to be between 28 and 21.
No, actually, I was about to do the sum. Actually, that was why I muted myself to calculate all the whole temperature for this one. Because I think
Exactly.
yeah.
So the right thing to do is just add everything up. Forget the temperature language that came with it. The normal map reduce syntaxes. It will sum up everything to aggregate everything together, then give you the sum of all the values for that key as the final value for the key. So city 1 should be having a value of, let's say, 28 plus 25 plus 23 plus 26 plus 20. That will be the summed up value that the reduced function will produce for you. Density 2, the same thing also. So Richard, do you get it now? Do you understand what we mean by key value pairs?
Yes, it's clearer now. Thanks so much for the explanation.
Okay, yeah, you're welcome. So I would say we're already at the end of today's class. Like that will be all for today's class. So hopefully, you said?
I have a question.
Okay, I think I need noisy place. Can you just try? Okay, go on.
I also have a
At
question.
the latter part of the when you're talking about HBase and I was seeing them being like they're talking about only for structured data. But is there anyone that offer for any structures semi-structured and unstructured data?
Oh, anyone that works for semi-structured, structured,
And
and
unstructured.
unstructured data. In a way, I would tell you it is. In a way, that would be map reduce, because let me give you a simple scenario. Semi-structured data now, some people will look at it and tell you it is unstructured data. Then from another person's perspective, the person will tell you it is structured data. So let me give you a typical example now. So let's say I export my emails, or okay, I export the chat of you guys WhatsApp group chat. I export that chat as a data set. By the time I'll be exporting it, this is what will happen. Normally, ideally, the chat of your WhatsApp group chat should be classified as what? As unstructured data. Am I right? But by the time I'm done exporting it from WhatsApp, it is going to become semi-structured in a way. And some people will look at it and tell you it is structured. Machine learning enthusiasts, NLP enthusiasts will tell you it is structured. Why? Because the chat from your WhatsApp group chat now, it would have a column named as timestamp. Then it also have another column named as sender that will carry the phone number or the display name of the person making that statement. Then you will now have another column called messages. So it's that messages that will now carry your chunk of words, your sentences, that will now carry it for every row, every entry. So if an NLP enthusiast should see that now, will be like, oh, this data is structured. It is a structured data, because for someone like him to clean that type of data, he just needs to call the peculiar Python libraries to bag those words together, give them different bags of words, then give them values or integers for every appearance of every word, then remove stop words from that data, then be able to use it maybe for sentiment analysis, for maybe classification, or anything he wants to use that data for. But let's say someone that is a business person now, the person can tell you that data is semi-structured or if not unstructured, because they wouldn't really know how to process the data that much. So they will just like it's semi-structured or unstructured. But a machine learning geek or an NLP geek will tell you the data is very clean, it is neat, it is a structured data. So for your question now, that type of data now, I can pass it into MapReduce. Can you see it now? I can pass that type of data into MapReduce. So in a way, if I pass that data into MapReduce, definitely it is still unstructured data, it is still semi-structured, and to some people it is structured. So I wouldn't necessarily say there is a, I don't know, I can't say there's a particular component, there's a particular component or element of the Hadoop ecosystem that can work on all types of data sets. But as you work, as experience comes in the field, you get to meet new technologies every day. So I can't give you a peculiar answer to that. But I'm just giving you the MapReduce example now and your WhatsApp group chat example that yes, it is possible. I hope you're able to get me, Sunday.
Yes, I do.
Okay. So does
Can
anyone
I
know
ask a question?
Okay, go on.
Okay, I noticed that we skipped some of the knowledge check, and I would like to know, is there any way we can assess it if we try to go through it on our own, such that we'll know whether our approach to the question is right? Is there any way we can?
Okay, so the thing is, the reason why I skipped some of those knowledge check is because having gone through them, I know that if I go through each and every one of them, I wouldn't be able to touch the major parts of today's class within the time frame. Yes. Why? Because they are, how would I call it? Most of the knowledge check questions, they are discussion questions. They are questions that require you guys discussing, me to also discussing with you guys, sharing ideas. Like you said, they are approach-based questions. There is not necessarily a peculiar way to a certain approach. Yeah, that's why. So, and if we do that, I don't know. So one thing you guys can do is probably in group discussions, you can just go through it together and just, okay, what do you feel about this? What do you feel about? Then if probably maybe you want to seek someone's approach, you can either reach out to me, reach out to Edward or Blessing, anyone. Yeah.
Okay. Okay. Also, sorry, while we were looking at the age base, there was a point I noticed there. It mentioned that it has low latency. So can we say that that is a shortcoming of age base?
No, low latency means software engineers are always looking for things that have low
Okay.
latency. So let me explain what latency means now. So
Okay.
latency basically in software engineering means time to complete an operation, time for memory to run some tasks. So if you
Okay.
say it has low latency, meaning it takes lesser time to run things. And if you
Okay.
notice, that's why we use HBase for streaming data, for data that is arriving at a very fast velocity, at a very high rate. And then that's why it is, if you notice, we use HBase for real-time analytics. Because of the fast processes and the fast computing rate, we can always get our response fast also. So low latency, and again, if you notice, when they taught you guys about distributed computing and parallel computing, I don't know if they made mention that parallel computing has low latency than distributed computing, in which Hubert made explain to us today that for parallel computing, as we all know, the memory and the processors, they are all in the same domain. So meaning the processors share the same memory. So that way, for data delivery to the different processors wouldn't take so much time. But for distributed computing, it's like we have a lot of computers that are connected. Each of the computers have their own processors, have their own memory. Then they are not connected in a certain network. So data
Okay.
delivery in that kind of setting will take so much time. So the latency is high. Low latency means, in fact, we actually look for low latency. Then if you also look at, okay, if you also look at your network categorization now, if you look at your 2G, 3G, 4G, 5G, they will tell you your 5G has low latency. Why? Because it takes lesser time for it to execute operations compared
Yeah.
to your 4G. Yeah.
Okay. That's right. Thank you, sir.
Yeah, thank you very much. Thank you guys for coming. I don't know if I'll be seeing you guys next, but I don't know. So it depends on how it is. So I believe some people will be is going to their data analyst class, and some people will come into the data engineering class. Yeah, from now, because I know this is, I don't know, I think this should be the last topic that the last class, the last topic in terms of data engineering curriculum you guys should be having together. But I don't know, sure. Depends. But I know I'll be seeing more of the data engineering guys. So thank you so much. If you have any question, let me know. Though time has gone, I'm done for today's class.
Okay, hello.
Okay, Edward is here.
Okay, thank you, Temilola, and to everybody on the call. Thank you for your time. I sincerely appreciate Temilola's time for finding time out of his busy schedule to stand in for this class. Thank you once again, Temilola. So, did anybody introduce Temilola to you guys? Hello? Hello?
He introduced himself during the first class.
Oh, okay. So let me now introduce those guys in the data engineering class. So you're seeing more of him. So both anchor the session, but to everybody. So Timola is one of they'll call them the most acutest brain. So sharp brains and like the strong hands we have on Octave team. Is working currently on a project with Coronation Merchant Bank and is helping with facilitating some cloud services. So you have the best hand to learn from, and I'm very sure he's going to give you his best too. So Temilola, I will say thank you once again. Sincerely, I really appreciate your time for this. So and to everybody, thank you for coming. In case I don't know if Emmanuel is on this call. Let me see. Emmanuel is on this call. Okay. All right. There's no problem. So Temilola,
Yeah.
you started the class, so you have the right to either continue or dismiss the class. So,
No,
but
we
thank
are
you everyone
done.
again.
Thank you
Thank
very
you
much.
everyone.
Thank you, Edward. Yeah. Bye bye. We'll see some other time.
All right. Bye, guys.
I want to add that I really enjoyed this class before you leave.
All right. Thank you guys very much. Enjoy the rest of your day.
So, Sunday, are you starting the call?